Thank you. Okay, welcome back to AI4ESP workshop. We have a couple of exciting speakers this morning, and we will start here, and then we will break out to our two sessions for the day. So to get us started, Laure Zanne is a professor in mathematics and atmosphere ocean science at the Courant Institute at New York University. Her research focuses on the dynamics of climate system, and the main emphasis of her work is to study the influence of the ocean on local and global scales. Prior to NYU, she was a faculty member at the University of Oxford until 2019 and obtained her PhD in 2009 in climate dynamics from Harvard University. She was the recipient of the 2020 Nicholas P. Fofanoff Award from the American Meteorological Society for the exceptional creativity in the development and application of new concepts in ocean and climate dynamics. She's the lead principal investigator of the NSF NOAA Climate Process Team on Ocean Transport and Eddy Energy and M² lines, an international effort to improve climate models with scientific machine learning. She currently serves as an editor for the Journal of Climate, a member on the International Clyvar Ocean Model Development Panel, and on the CESM Advisory Board. Laura, thank you for joining us, and we are looking forward to hearing you.
Great, thank you very much for the intro, and thanks for inviting me. Definitely very exciting to be here at this workshop. So I've watched quite a few of the videos before. It's a lot of excitement and a lot of great people talking about a great progress and how to use AI, in earth sciences in general. So here, what I'm going to do today is I'm going to focus on how we can use AI and machine learning to improve climate projections with a focus on the oceans. As Nikki mentioned, this is really kind of, my area of expertise in quotes, how the ocean works and how they function in the climate system and how we can improve their representation in climate models. So it's the work that I'm going to present. It's joint work with Tom Bolton, Arthur Guillaumin, Andrew Ross, past and current group members. But I'll also introduce M² lines that Nikki mentioned during the introduction, which is a large international collaborations to improve climate models. And so I'll talk a little bit about the project and again, some of the results that I'm going to highlight for the oceans are part of this project, M² lines. Okay, so, of course, with this audience, I probably don't need to motivate it that much, but nonetheless, how can we leverage AI for ocean sciences in general? And so, one of the main reasons is, of course, climate is changing and we can measure those changes over time. And so trying to pull out all the tools and all the expertise that we have to actually understand and better predict or at least adapt to climate change is definitely urgent. Second is increasing computing power, right? So again, this is kind of what has driven the increase in the use of AI in general, not just in our field, but also the amount of data that we're getting and the quality of the data, right? So down here is kind of a nice little plot of the amount of data over time. We can see this kind of immense increase, especially, for example, in the ocean, where we have now a lot more data telling us how the temperature is changing over time, how much ocean warming we've been experiencing. So really a vast amount of data, both at the surface of the ocean and the interior. Lots of satellite missions, right? And so that's been very exciting as well, being able to have high accuracy, really dense estimate of what the surface of the planet is doing in terms of temperature, and sea surface height, which we, use a lot. But of course, there's also a fair bit of data that comes out of models. And so it's kind of a nice growth of, NOAA archives and projections in terms of the amount of data that's being stored. And those kind of green bars are model data, right? So we can run simulations, and we have more of those simulations. So we're getting more and more data directly from observations, but also from simulations as well. And so how can we use, all of those, all of that data and all of this computing power to actually do something when it comes to ocean sciences and climate science in general. So we can speed up computation with AI, right? And so I think some of that has been discussed before. We can come up with better reconstructions. So say, with satellites, we measure the surface, but that's not enough. We know that a lot of things are happening below the ocean and below the surface in the interior of the ocean. So kind of the inference problem, trying to reconstruct spatial and temporal, data sets is important. That has been happening quite a bit even before, machine learning tools, but that's something we can really improve on. We can do forecast and predictions, right? So basically you have more data, and so you can create, models that are purely data driven, that you can literally directly learn from data and make predictions from it. But the part that we're focusing on is this kind of last bullet point over here. And so people sometimes call it hybrid modeling, how you bridge, machine learning and AI together with physical models. And so what we focus on is actually coming up with better subgrid parameterizations in climate models. So the processes are too small to be captured by the model resolution. And basically, we're going to try to learn from data using machine learning. And so that's what I'm going to focus on here. And so why do we care about this, right? So why do we care about subgrid parameterizations when it comes to climate projections? So here, what I'm showing are projections of dynamic sea level in 2 generations of climate models, CMIP5 up here, CMIP6 down here. And so if you look at this kind of multi-model mean in the CMIP5 and the CMIP6 of dynamic sea level, you see very low differences. There are some dipoles, in the North Atlantic and in the Southern Ocean, and we understand that the physics of it really well, actually. So this is, in the Southern Ocean, how the Ekman transport responds to the changes in winds in the Southern Hemisphere. Up here, it's related to how the ocean circulation is changing. So we have a really good understanding of the physics, and the model do a really good job. But on the right, what you see is the spread across models. So basically, how different is the magnitude of sea level projections in those simulations. And whether you look at CMIP5 or CMIP6, you get very low differences, right? So the same places where you get large signals, like the North Atlantic and the Southern Ocean, you get large spread. That means that the models differ from one another. And the uncertainty didn't go down, right? If you go from the previous generation of model to the current generation of models. So the spread did not decrease as we improve our simulation. And one of the main reasons is that that uncertainty is directly tied to some of the subgrid scale parameterizations we have in climate models, such as mixing in the ocean, for example, and convection. So many processes in climate models are not well represented, right? And so they lead to uncertainty. And so in the ocean turbulence and mesoscale eddies, clouds in the atmosphere, sea ice heterogeneity. So all those processes are too small. They're smaller than the grid box size of climate models that we have. And so they lead to uncertainty in projections. Second thing is, of course, we're solving equations on the grid. So we make approximations on the grid. So that's another source of uncertainty. So we have 2 pieces that makes our projections uncertain. One is numerics and the approximation we make by writing equations in a discretized way. And the other thing is we're limited by the resolution of the climate models that we run. So usually what we do is we try to come up with closures or parameterization of all those small scale processes that we can resolve. As I said, clouds in the atmosphere, mixing in the ocean, whether it's diapycnal or isopycnal. And the way we've been doing that traditionally for decades and quite successfully to some extent is come up with very simple, idealized mathematical representation of those small scale processes that influence the large scale climate. But as I showed you, right, traditional closures have struggled improving climate models and projections. And so the question is, can we do better now that we have more data and we have better algorithms? So what we propose is to develop data-driven, but physics-aware, meaning that we do embed some theory or some conservation to come up with better parameterization of subgrid scale processes, especially in the ocean, like turbulence. And so really now we interrogate the data with machine learning algorithm to come up with better representation of small scale processes that are not represented in climate model. And hopefully along the way, we learn some new physics directly from the data rather than making assumptions about what a process should look like mathematically. So, this approach of coming up with, processes that are too small to be represented in climate model has been around for a while in the atmosphere, radiation, atmospheric convections, rain processes. So here down here, you get a few examples, really tackling it this way. And for ocean processes, so, my group has been very involved in coming up with parameterization for ocean turbulence, and a few other examples as well. And so really there's a lot of momentum, so to speak, in trying to use machine learning and data to come up with better subgrid scale parameterization. We don't want to replace the whole climate model, right? Because we have equations and we know them quite well. But there are those pieces at the end that are too small to be resolved, where data and machine learning could help us over the traditional mathematical closures. So that's what we focus on. And that's really what M² line is all about, right? So how can we improve the scale of those, existing climate models in existing centers to do a better job and basically improving their skills and having better representation of subgrid scale processes. So machine learning is supported by Future. So we're very lucky to get the support to really try to blend data physics and scientific machine learning to improve climate models. So we're about 30 scientists in the US and France. We're experts in climate science, so atmosphere, ocean, and sea ice dynamics. We have experts in machine learning and climate model development at 3 centers, NCAR, GFDL, and IPSL. So it's really bringing the community together, from people who do theory and understand climate science to people who come up with new machine learning algorithm, all the way down to real climate model developers, so we can actually feed that directly into climate models. So we're going to learn a lot of different subgrid scale parameterization, both in the ocean atmosphere and at the sea ice interface. So as I said, that can include atmospheric convection, boundary layer processes in the ocean, vertical mixing, mesoscale eddies, sea ice heterogeneity. So we're really trying to capture a wide range of subgrid scale processes to really improve climate models at the end of the day. So really, the scientific aims at the end of the day are no different when you use machine learning than when you use any other tool. The project, and I think our science in general, is driven by 3 goals, right? One is to aid physical mechanism and interpretation. I want to learn new physics, or I want to do better physics to some extent. And so AI and machine learning is one tool to do that. At the end of the day, everything we do, we have to test the robustness of the method and the results. And at the end of the day, we also need to validate, verify, and have some uncertainty quantification of all of our models. And that's true no matter which scientific, which scientific goal you're trying to go after. And so whether it's this or something else, this is really what we strive for. Better physics, robustness, and reproducibility, and making sure that everything we do is, can be, validated and verified across. And so I'm going to show you a few examples of those 3 bullet points with some work that we've been doing using machine learning to improve subgrid scale parameterization of ocean turbulence. So first, validation, uncertainty quantification. So when you learn something from data, you need to make sure that it actually makes sense and you can quantify uncertainty with it. So here's an example where we learn a parameterization of ocean turbulence or backscatter. So basically how to represent the effect of mesoscale eddies that are not well captured in climate model using machine learning. So we took velocity input from realistic models in 4 little regions, and we trained a machine learning algorithm to predict subgrid forcing, but rather than just predict one quantity, not just what is missing at that grid point, we're actually trying to capture a PDF. So we're trying to capture a probability. And so what does that mean by that is, I'm creating a model of a missing term, but it's still a representation, it's still an approximation, even if it comes from data. So it's still a bit uncertain. So, this kind of, rather than learning just the mean, we learn the mean and the standard deviation. And that's one way for us to actually capture the uncertainty in the parameterization that we're representing. And so we can, change the loss function in the learning algorithm. So then every time that, we use velocity as an input, our output is going to be a prediction of the missing subgrid forcing, but also the spread around it, or the standard deviation around it. And so that's one way to, ensure that the model that we're creating have some uncertainty quantification associated with it. But we also want to make sure that whatever we learn can generalize. So what I mean by that is that we need to validate against, simulation that we didn't use for training or in different dynamical regions. So here we only use 4 dynamical regions to predict the subgrid forcing. Now, how do we do when we look at the globe, right? By only training on those 4 regions, what I'm showing you here is the R squared. So basically, if you have a number that is high over here, that means we're doing really well. And if it's down here, that means we're doing poorly. And so even poorly here is still 50% skill. That means no matter what, the algorithm, the machine learning algorithm is doing a really, really good job at capturing this kind of missing forcing pretty much everywhere, in the globe in that simulation on data that it hasn't seen before. The places where it does poorly, it's high latitude where it's covered in ice. So the physics is quite different at that stage. And that's not hugely surprising. Now here, what we've done is, we learn on a control simulation. So now what happens if we checked, in a simulation where CO2 is double, because I want my parameterization to work in different climates as well. And so here, if we look at the R squared, so again, the skill of that parameterization, without relearning anything, we can see that it transfers very well. So there's no degradation in skill from this machine learning algorithm that we used. And so that's great news, right? So you could say, wow, that's awesome. Deep learning does an amazing job. So in this case, I didn't tell you, but we're using a CNN, so convolutional neural network. So it does great, generalize really well overall. And, I have an uncertainty quantification associated with it. And so, you could say that this is all nice and well. But the problem is I have no idea why it does well because too many parameters, lots of stuff happening, very difficult to actually aid with physical mechanism, even though we learn a lot from it. So a second technique that we're using is trying to discover equations. So a lot of people have been using, equation discovery to show that with data, you can actually learn equation of systems that you know. So in our case, we try a different approach. What if we try to learn an equation for something we don't know, which in this case, our subgrid parameterization of ocean turbulence. So the process is the same. We start with data and we give the algorithm some data and we ask it to learn this kind of missing, forcing or this parameterization of ocean turbulence. But rather than, outputting, thousands of weights like a neural net that is very complicated, we actually only ask it to have some weights that multiply some basis function. So a library of function that we give the algorithm, like derivatives of velocities or squared of velocities, shear, deformation, things that we think are physical. And we ask the algorithm to actually prune this set of basis function and give us a subset that will faithfully represent this missing forcing, this kind of ocean parameterization of turbulence. And we end up with something like this. I'm not going to explain what it is, but it's a very elegant formula that is symmetric and captures part of the physics of turbulence. Depends on vorticity and deformation. And this is really how energy and momentum is being transferred between scale. So now in this case, machine learning gives us an equation that we can go after the fact and actually try to understand from a physical perspective. So this is one way where machine learning and data can help us with physical understanding and interpretation in a different way than we used to before. Now, finally, testing the robustness of the methods and the results, right? All of that was done, was basically done offline. Now, what happens when we implement things within climate models? So that's pretty hard, obviously. So we started with a very idealized model. We take our learned subgrid parameterization and we implement it in an idealized model. And the first thing that happened is almost the same no matter what, as the model blew up. So we had a lot of numerical instability, even though we actually tried conservation of momentum and things like this. But nonetheless, if I compare a coarse resolution without a parameterization with a high resolution, obviously we have less energy, less momentum, and so on and so forth. But when we implement the parameterizations, whether it's this kind of equation discovery that I mentioned about, or a neural network that we trained on, we have improvements, right? But again, there are some numerical instability and there are some ways to go around this. So at the end of the day, we need to go all the way from offline to online implementation to make sure that whatever we do is actually robust and can be implemented. So now I'll show you some good and the bad, but at the end of the day, right, we need things that we're going to learn from different data sets where we can understand everything we do. And so far, I picked and choose. I took a data set, implemented another model, then I tried different data sets, but as a community, we haven't come up yet with something, with proper benchmark that we can go from beginning to end. And so this is something we're doing as well, as part of M²9 is really having some standardized benchmark. Starting from simulation, we understand very well, and coming up with different definition of subgrid forcing. What do we mean by it? Different machine learning, different loss function, different architecture, different tests, offline and online. And it's very important that we have something robust beginning to end. And so again, we've been going through all those examples that I showed you before, training neural network, doing equation discovery to have really benchmark beginning to end that we can trust. And I think if we want to improve climate model, we need to make sure that we have something that is transferable from one model to the next. So really, I think something that is robust overall is absolutely critical. So at my 15 minutes now, so I'm just going to sum up. And so overall, parameterization of unresolved processes are still in demand and will be in climate model for a long time. They create, spread and uncertainty in projections. Machine learning and data can improve on this domain knowledge. And so for backscatter, I show you generalizes quite well. We can help with, discover new equation and relate it to some physics that we know. There's some degree of non-locality in the parameterization. I haven't talked about this. And the result improve, online simulations. But overall, there are still many challenges ahead. But I always feel like we can summarize them in 3 key principles, right? We need to make sure we aid with physical mechanism and interpretations, that we have robust methods and results, and that we can validate, verify and have some uncertainty quantification if we really want to improve projections. So I always see, challenges as opportunity, and it's finding the right blend, of physics plus machine learning as a tool to help us move forwards when it comes to improving climate models. So I'll leave it at that, and thanks a lot.
Thank you very much, Laura. If you will check the chat, Sven had a question in there, and if you could answer it there, that would be great. Okay, for our second presentation, Katie, do you want to share your screen real quick?
Sure.
Make sure you're ready to go. So Katie Dagon is a project scientist in the climate change, whoops, I lost my notes, climate change research section of the Climate and Global Dynamics Laboratory at the National Center for Atmospheric Research. Her research interests center around the impacts of climate change on land-atmosphere coupling and the terrestrial hydrological cycle. She's also interested in uncertainty quantification and machine learning approaches to understanding sources of uncertainty in climate models. Katie received her PhD in Earth and Planetary Scientists at Harvard University in 2017, where she investigated the climate impacts of solar geoengineering. Thank you for joining us, Katie.
Thanks, Nikki. Yeah, thanks so much for the invitation. I've been able to participate in a lot of the sessions so far. It's been a really interesting workshop. So this is kind of a nice follow-up to Laure's very nice talk, also a perspective from a climate modeler. But I'm going to try to frame it in terms of both grand challenges that we can think about for the rest of the workshop, and also lessons learned from some of the machine learning projects that I've been involved in. So the overall question is kind of how can we leverage machine learning for climate modeling? And I'm going to structure this talk by going briefly through a couple of research highlights from work that I've been involved in at NCAR, and then end with some lessons learned and grand challenges going forward. So the first project that I want to talk about has to do with machine learning for model emulation and parameter calibration. This is actually something that we've heard quite a bit throughout the workshop. So I think it highlights it as a really nice cross-disciplinary topic. But in particular, I was thinking about land modeling and biophysical processes for this project. So the motivation is that we know that these models are complex and we'd like to better understand their uncertainties, especially their parametric uncertainties. At the same time, traditional parameter calibration methods can sometimes be costly and inefficient. So our approach here was to train an artificial neural network to emulate the land model, the land component of the community Earth system model, in order to perform efficient parameter calibration. And this approach helps quantify parameter uncertainty because the emulators allow for many fast computations at different parameter values. The results can then be optimized to fit different observations. So there's a lot more detail in the paper cited here. But I think one interesting question going forward is sort of to think about what we're gaining using machine learning for calibration over traditional hand tuning methods. This is something that's come up in the conversations that we've been having in breakout. And also how do we go beyond that sort of comparison? What's next to look at? But I also want to highlight what we can learn from this. So interpretability can shed light on physics. Here I'm just showing a relatively straightforward interpretability method, which is a feature importance test or permutation importance. So for the 2 variables that we were looking at with this project, which was carbon flux variability and water flux variability, we can sort of test the importance for the different parameters and ask, the emulator, or test which parameters are most important for the skill of the emulator. And so that's what's shown here. And what's interesting is then we can sort of look at those processes connected to those parameters more closely. And so that tells us something about, for example, plant hydraulic stress in the model or stomodal conductance. That also helps us learn about how to better define parameter ranges, how parameters interact, and it can hopefully help inform future calibration and uncertainty quantification efforts. So moving right along to the next project that I want to highlight, this has to do with the detection of extreme events. So the motivation here is that we know extreme precipitation has very significant consequences, but it also originates from many different types of sources. And we can also leverage the existing AI and ML work of pattern classification and feature detection to think about some of these extremes. And so our approach here was to apply and develop different deep learning algorithms to detect features like atmospheric rivers, tropical cyclones, mesoscale convective systems, and fronts in different climate model simulations. And so the animation I'm showing is where we've applied the ClimateNet algorithm, which is developed by the Berkeley Lab group. Probably many of you are familiar with this work, to detect ARs and TCs globally in high resolution coupled community Earth system model simulations. And I want to emphasize that this is not a particularly new machine learning for climate approach, but we are interested in sort of what we can learn from applying these methods, both on the scientific side in terms of the causes of extreme precipitation, but also what we can learn from the machine learning itself with respect to knowledge discovery and hypothesis generation. So I will kind of highlight that on the next couple of slides. So domain knowledge informing machine learning training. So we have been able to detect atmospheric rivers and tropical cyclones using these trained models, and they're trained in particular on 4 different input fields. If you know about the ClimateNet project, it was kind of a crowdsourced, expert labeled training data set that was developed, but there's these 4 input fields that are used. But we also know from projects like ARTMIP, which has to do with atmospheric river detection, that sometimes there's only one field in particular that's important to detecting atmospheric rivers, just showing an example of that on the top here. So what we were able to do is actually test the training of the retraining of this deep learning algorithm to detect atmospheric rivers using only a single input field, which is that vertically integrated precipitable water, which we know from projects like ARTMIP is usually the most important field to detect atmospheric rivers. So it's a nice example of sort of the domain knowledge informing the machine learning training, and also an example of sort of transfer learning when we're testing out the importance of these different input fields. The other sort of follow-on to this work that I want to briefly mention is hypothesis generation. So we are also working with a different machine learning algorithm that's applied to detect different weather fronts over North America in climate model simulations. This is developed by Jim Baird and Ken Kunkel at NC State. And so we're able to apply this to detect these weather fronts in our climate model simulations. But we're then able to sort of take that detection and compare it between sort of historical simulations and future simulations, for example, with RCP 8.5, future climate forcing, and actually look at the changes in the detected fronts. So here I'm showing the changes in front climatology seasonally, so how many fronts are passing per week. But then take those results and think about generating hypotheses for the mechanisms of change. So for example, looking in June, July, August, we're thinking about how to explain the decrease in detected fronts and possibly connecting that to the northern retreat of the jet stream, which is shown in other CMIP model studies to possibly be a mechanism associated with climate change. While this is still very much an active area of research, and we need to sort of think about how this compares, this response compares in other models, it's kind of a nice way to use the machine learning results to generate hypotheses. Okay, the third research highlight that I want to mention has to do with water cycle predictability. And this is work led by Maria Molina. So thanks to her for providing these slides. And so the motivation here is that precipitation is a poorly predicted phenomena on subseasonal timescales. The figure that I'm showing here is just an example of the anomaly correlation coefficient across different iterations of CESM, really showing how low that correlation coefficient drops when you look out sort of further than week 1, 2. But we hypothesized that the limits of predictability for example, modes of variability and their associated impacts can be expanded and identified using machine learning. And so there's kind of a twofold approach here. And thanks, Maria, for providing this graphic. So the first approach that we could take is we could learn the connection between the future state For example, like looking at time here on the x-axis, and some prior observations or initial conditions. So using machine learning to make a forecast. The other approach that we could take is looking sort of at the same point in time and using machine learning to correct forecasts, so bias correction. And I also want to mention, since I have to kind of go through this quickly, that more details on this work are highlighted in the white paper that Maria and I co-led. But one approach that we'd like to take with this work is to investigate prediction skill with explainable AI. So the idea here is train the machine learning using the physically relevant fields that we think are important for predicting, for example, modes of variability like Madden-Julian oscillation or El Nino Southern oscillation. Think about the impacts, temperature and precipitation, but then use in explainable AI methods such as saliency maps or LRP to generate heat maps using the input fields. For example, the great work that Libby Barnes and her group are doing on these explainable methods to really understand the sources of prediction skill and potentially think about windows of forecast opportunity. Okay, so I think I'm at about 10 minutes. So just to sort of summarize what I've talked about so far, some of the lessons learned. So for parameter calibration, we used interpretability to learn about parameter ranges and interactions, and hopefully informing future calibration efforts. I didn't really have time to mention that we're trying to automate these workflows so that we can share them with the community, because I think it's an important need that the community has to be able to calibrate particular regions of interest to their observations. So for detection of extremes, we talked about how we were able to incorporate domain knowledge to select the input fields for feature detection, and also think about hypothesis generation from the results. And then for water cycle predictability, we're hoping to use explainable AI to highlight precursor mechanisms and also maybe some knowledge discovery to reveal forecast windows of opportunity. And then I just want to step back and take a bit of a broader scope for the last few slides here. Another project that I'm involved in at NCAR is the Earth System Data Science Initiative. And this initiative is really driven by this need to build an inclusive socio-technical network across NCAR to promote sharing data workflows and solving problems together. So what I mean by that is this is motivated by the fact that data wrangling consumes a lot of our time. I'm sure many of us can relate to that. We should be hopefully sharing and reusing parts of our workflow instead of creating things from the ground up. I think for relevance to this audience, that will allow us to be well poised to tackle problems in AI and machine learning. And so there's more information on the website. And right now, this is a team that's sort of spread across 2 different labs at NCAR, but we're hoping to expand beyond that. I also just want to say, like, there's no shortage of tools to help us sort of tackle these problems, but the goal of this initiative is more about the communication and bringing people together and bringing software engineers and scientists together to solve these problems, which I think is very relevant to the conversations we've been having at this workshop. Okay, so I want to take my last few minutes to just summarize with some grand challenges. And I want to note that many of these points have been inspired by the previous week's plenary talks and breakout discussions. I think this is kind of the advantage of being the last plenary speaker, is that I actually get to learn from the data that I've seen so far. You could also think of these as guiding principles. They're going to be less specific on the science, but sort of ways that we can think about moving forward. Okay, so the first thing I want to mention is just, making sure that we're being critical of the results. So what are we learning? Are we advancing the science? This, image here is sort of thinking about the analogy of hammers and nails. I think it was Bill Collins who brought this up, but, are we just using our machine learning hammer, looking for nails, looking for problems? We need to make sure we're being critical of what we're using machine learning for. But at the same time, and this might sound like it's an opposing viewpoint, but I think they go hand in hand. I think it is important to take advantage of the current progress and opportunities, not to necessarily wait too long for the field to catch up. I think that was something that Prabhat brought up on the first day. riding the current wave of AI and ML enthusiasm. The momentum is there, so how can we take advantage of it? Learning from the data. So I just want to acknowledge that I think there's a trade-off between physics-informed machine learning and knowledge discovery. So while we do want to use physical constraints, of course, they're very important, we also want to let the machine learning sort of reveal new mechanisms to us as applicable. Democratizing software. So this is a really, really interesting point, I think builds on the previous slide where I was talking about the Earth System Data Science Initiative, and also lots of conversations that we've had throughout this workshop, providing accessibility and entry points for domain scientists to explore ML techniques, as well as vice versa, opportunities for machine learning experts to explore the science, to sort of encouraging those collaborations. Model maintenance. This was, I think, a really nice point that Grace Kim brought up on the first day. So sort of balancing the scientific culture of static publishing where, we publish a paper, and it's, we don't necessarily return to that to update the model, but that, as we receive new data, that might be an interesting thing to think about. This also, I think, relates to, not just publishing successes, but also talking about what didn't work. So publishing failures and lessons learned, that could actually be really helpful for the community. So I think co-design is something that's come up several times throughout this workshop. I thought that Rob Ross had some really nice points about this in his plenary. So engaging experts early in the process, reaching across disciplines, this will make us sort of well poised so that the machine learning algorithms are ready to utilize the data. And then finally, I just want to mention environmental justice because I think it's something that we haven't heard a ton about during the breakouts, but we heard from Gary Gernot on the first day talking about how this is going to be really important to position the community to tackle these complex issues. Amy McGovern also mentioned AI and ethics in the very first plenary. So I thought it would be kind of important to bring that back up here at the end and think about that going forward for the rest of our conversations. Okay, and if you don't remember anything else about my talk, just refer to this XKCD diagram. So thanks very much for your attention.
Thank you, Katie. That was great. All right, everyone. Katie might take a look at the chat. I don't think we have anything right now, but if you have a quick question for Katie, go ahead and put it in there. We'll stay on for a couple of minutes. And everyone else, have a great break, and we'll see you back on at 15 till.